think we'll have an early lunch today. I just gave a talk at a meeting in Japan that Brian Warner and I were at. I had twice as long a talk in 10 minutes to give it. So maybe I should have reversed the topics and given that one here because it was a real race, but this should be a little more leisurely. The problem I want to address today is in doing Lightcurve observing, and you've seen a few examples of that earlier today. If you have a nice long body like this and you rotate it and imagine the light coming off of it, proportional more or less to its size, it gets a lot brighter and a lot fainter, and it does that twice per rotation cycle. Now, if you take a fairly, a red potato that's not very irregular, and you spin that around and ask the question, can you make the assumption that 2 bumps in the light curve equals the rotation period? The answer to that is no. And so the question that we want to address is, at what point can you be sure that bimodal light curve is the rotation period, and when do you have to be cautious about that? Let me see here if I got this right. Okay, the first thing we do is we make an assumption for this simple analysis of what's called geometric scattering. That is, that the intensity of the light that you see from an object is proportional to the cross-sectional area at the moment you measure it. So if you're looking at a broadside, as in the left image there, of an ellipsoid, you're seeing a bigger area, and as it rotates around, it gets smaller and smaller until you're looking end on, 90 degrees around. That's the minimum light. And the amplitude of the variation is simply proportional to the ratio of the 2 short axes compared to the ratio of the long and polar axis. That turns out to be very close to true, even for not ellipsoidal but irregular shapes, if you're looking at a very low solar phase angle, so kind of like the full moon. And you can see why that's so just imagining the moon. When you look at the full moon, it's just sort of this circle of more or less equal brightness. When you look at a quarter moon, the terminator area is a whole lot fainter, and so geometric scattering doesn't work at 90 degrees. But it does work pretty well for asteroids as well as for the moon when you're under, say, 20 degrees or so phase angle. Okay, the next question is, suppose we had shapes that are not circular or elliptical, but rather maybe more like a cube or a triangle or something like that. You might imagine that a triangular shape, when you rotate it, would give you 3 bumps per cycle, but no, it gives you 6 bumps per cycle. It turns out that the fundamental frequency that you would see from a triangle gives you the 6th harmonic. A square does give you the 4th harmonic. The 5th pentagon would give you the 10th harmonic, and so on in the table. In the last column of the table there, I've listed in magnitudes the maximum amplitude that you would get, which is simply the line across the figure when it's at its most broadside or its widest versus when it's at its narrowest. So if you imagined a prism of that shape rotating and at 0 phase angle, that would be the maximum amplitude you'd see. Now, it turns out that it's not a pure sine wave. Here, this just summarizes the amplitudes by harmonic order. So the 2nd harmonic can be arbitrarily large amplitude. 4th harmonic is about 4/10 of a magnitude, a little less. 6th harmonic is only 0.15, and after that, the amplitude is so low that almost anything can happen. Here is just a picture. This is the geometric shapes of the perfect square, triangle, hexagon, etc. This is what the light curves look. Notice the magnitude scale over there, and by the time you get up to the top one there, which is the pentagon one, that turns out to be, it should really be the 10th harmonic, I believe, but the other ones you can see, even the 4th harmonic is not a very big amplitude. It's only about the average of asteroid amplitudes. So fully half the asteroids you might chance to observe will have a larger amplitude in that, and the bimodal solution is the only one that could work. But for the other half of the asteroids, things can get kind of confusing. So let me show you a couple of examples here. The first example I'll show is an asteroid named Umera. And when the observations first came in, Adrian Galad in Slovakia took these observations, and it looked like the period was 1.7 hours. Now that's really provocative because almost no asteroids spin that fast. Now, the largest asteroids that spin that quickly are under 1 kilometer in diameter, most of them under 100 meters or so in diameter. Well, this guy's about 10 kilometers in diameter, and that would be very provocative to have such a short period in what we normally think of as a rubble pile or a fluffy body. The regolith would just simply fly off the surface. And if it's regolith all the way to the core, then the whole thing would come apart. So that was quite a provocative thing. And if you look at the lower curves down there on the bottom, that's plotted with a double period of 3.4 hours, which would be a perfectly ordinary period for an asteroid, but it happens to have about 6 extrema, and that seemed very unlikely. So Adrian went out and observed it again the next time in 2009, and he got the very same pattern. That's kind of that 180-degree problem. But if you look carefully there, you can see some subtle differences around the minima. If you look in particular, these two minima here are almost identical, and the ones over there are really quite unidentical. And when you composite that at half the period, that puts those one atop the other, and it doesn't look like it's that bad a fit. But when you plot it out separately and you have enough data, you can actually see that they are different. And then if you go back to the 2008 curves, you can see that that pattern actually repeats. If it repeats enough times, you begin to believe that it really is that longer period. So after hammering this thing an awful lot, and there's still one more apparition in 2011 that was observed, and it fortunately wasn't the 180-degree problem, and it actually revealed a pretty good difference. So we resolved this one, but if you just casually observe on a couple nights and put together a composite on one try, you could be fooled. So sometimes it gets difficult. Now here is a real strange one. This was observed by Brian Skiff at Lowell Observatory, who was mentioned in the earlier talk on the Lowell Amateur Collaboration Project. And this, in fact, was taken, the original Lightcurve was taken on the Lonios telescope at Lowell. And when Brian Skiff put the Lightcurve together, he had this thing that has a full magnitude of amplitude, and you can start counting. I don't know how many extrema there, like 6 or 8 or some very large number. Well, that's geometrically impossible at low phase angle unless you had flat mirrors or something on the asteroid to do really weird things. When I looked at this, my first thing I sent back by email is that's impossible. That just can't be. And so Brian kept pounding away, and others, Brian Warner, I think, joined the fray, and various other people, other observers. And after we got enough observations, Peter Pravec over in Andrejev in Czech Republic took a look at it to consider that it might be what we call a tumbling asteroid. That is a non-principal axis rotator. It's kind of like throwing a brick in the air, you know, and it's kind of tumbling and spinning, not in a regular way. Well, nature really threw us a curveball here. There are two periods. That is the period of what we would call nutation or wobble, and the second period is the actual axial rotation period. Those two periods are almost exactly commensurate with one another at the 5:3 ratio. So after 5 cycles of one of the periods and 3 cycles of the other period, it repeats. And so this longer period, this 8 or so hour thing, is really 3 times and 8 times the true periods of the 2 complex rotation periods. And when you sort the whole thing out in that bottom figure, you can see that there is just a single rotation and then this other thing that's going crazy. So this is multiple rotations composited together, and if you could look really closely there, there's a whole bunch of little fine lines that connect the points very, very accurately, so the tumbling solution fits extremely well. And Brian Skiff was not, in fact, going crazy as he thought he was. He thought he had completely lost his skill as an observer. No, he actually had done very, very well. Okay, just to summarize and conclude here, when you see a low amplitude, and I kind of take as a rule of thumb about 0.2 of a magnitude or so, you have to beware the number of extrema per cycle could be 3 or 4 or 2 or 1 or just about any number, and you really have to observe very thoroughly, very accurately in order to decide what the true period is. Then for large amplitude of variation, if it's more than half a magnitude or so, then the light curve really must be just bimodal, that is 2 extrema, and if you see something other than that, then it almost certainly is an indication of a tumbling asteroid. And that can happen with very slow rotators where it's really a big job to get enough data to fill in all the gaps, and after you fill in all the gaps, you got to do it again to see if it tracks again the second time, and like as not, it won't. And so it takes a lot of observing. There's plenty of opportunity if anybody wants to join in the fray and observe these things. Well, I think that's it. I want to acknowledge and give thanks to all of my unnamed collaborators and observers. You can read all of those. That gives you an idea of how many people it takes to get a solid answer on a really problematic asteroid. Thanks.
Any questions?
Any volunteers?
Yeah. Alan alluded to his paper in Japan, and which is to say that if you use, as you go through in a period analysis, if you go with too high of harmonic orders in your analysis, you can start latching onto noise and get false answers that way.
Yeah, for sure. There is a pattern when you start seeing things like this. If you do a second order solution and get 2 or 3 possible solutions, then you do a third or fourth or sixth order harmonic solution. If different solutions keep jumping out at you, different from according to the harmonic order you choose, you're probably looking at noise. That's for the really low amplitude ones, sparse data.
Anything else? Okay, thanks very much.